Press record button. Okay, great. So welcome to the next session of the PhD training in computer science, in data science. And today's lecture is devoted to different kind of distributions, introduction, what a distribution is, how can it be defined, and some connections between hopefully some unusual distributions. But quick reminder that we covered conditional probabilities up to now, and conditional probabilities are particularly useful if you are dealing with non-independent events, because then we can find the probability of the intersection or something that happens simultaneously for both events. And by Price-Laplace theorem, which is attributed to Bayes, but actually it was rediscovered and popularized, which is also important, by Price and Laplace. And it just allows us to find the conditional probability of A in terms of B through the opposite, the conditional probability of B in conditioned on A, using also probability of A and probability of B, which is the start of the whole new world of Bayesian statistics, which I might cover or touch a bit next semester, because it's indeed very fascinating. And yeah, there's lots going on. It's very much world in development. And indeed, the distributions that I'm talking about today can be very useful for Bayesian statistics because they can act as priors. The main problem was that it's hard to measure accuracy in anything, including probability theory. And that's why there are just many types to measure accuracy, which we've touched on. You're welcome to refresh your memory from the previous lectures. But let's move further from here. And well, another reminder of what was going on even before that. So probability theorem actually stems from Kolmogorov axioms. What Kolmogorov did in the 30s, he formalized whatever was guessed, known in probability theory, and formalized it in a way to make the whole measure theory, which was well developed by that time in mathematics, to make the measure theory applicable here. And for that, he introduced so-called probability space, and probability is the function, well, the last letter P in this triple, and this probability function should satisfy three axioms, which is positivity, unit measure, that the probability of the whole is 1, and additivity. But the basic blocks of everything is elementary events, which are also called atomic vectors, sample points, and they're just all possible outcomes of some kind of a model which is run once. Well, that's a very, very, very basic example in front of us. So suppose we are dealing with flips of a coin. Suppose we have 8 possible outcomes all in front of you. So what is the number of all possible events? And you're welcome to use the chat to answer this question. So how many all possible events can be built on 8 outcomes? So we have 8 outcomes, and all possible events are just all possible sets that we can make, or all possible combinations that we can create out of those 8. So any ideas how to calculate it? So for each element, and we have 8 elements, and for each element it can either belong to our set, our subset, or it can not belong. Which means that for every element out of 8, we have 2 possibilities, either to include it or not include it. So what do we think? What is the number of all possibilities? So since we have 2 possibilities, included or not included, that will mean that there will be 2 to the power of 8 possible combinations, or all possible events that we can build on this outcome. Okay, so the second situation, suppose we have the same 3 flips of a coin, but the question is slightly different. We all are interested in the number of tails. And then we have 4 different possibilities, or 4 outcomes: 0 tails, 1 tail, 2 tails, and 3 tails. So that's elementary events. And how many possible events can we build on those 4 using the similar formula? So last time we had 8 events, and we were able to create to the power of 8 all possible events. And now we have 4. So what will be the number of all possible events in this case? Yes, Alex, absolutely, that's right. So we have 4 events, which means that all possible combinations and all possible events built on those building blocks is indeed 16. So you see, even in the same experiment, we can get a different cardinality, or the different number of all possible events. And that is why, even if the experiment is the same, it's so important to see how we define our model and what we are interested in. So let's see how in maths it is defined further. We need to define probabilities, and there are broadly 2 wide types of probabilities: either discrete probability distribution, where we start from the building blocks and we take this number of primitive building blocks, as we just did, finite or at least countable. And then we define the set of all subsets, and as we've covered, it will be 2 to the power of number of elements. And in this case, we can just give every element a particular probability, because we know how many possibilities we have, such that the sum of them is equal to 1, to conform one of the axioms. That's all nice and easy. The question is, what will happen in the so-called continuous distribution if we cannot count all basic blocks? If we, for example, take those building blocks coming from an interval, and that's a non-trivial situation. Why? Because if we do a similar thing and assign some kind of probability to each of those elementary building blocks, then because we have an infinite number of them, they will quickly go above 1. Which means that we need some other way to define this kind of probabilities. And that was quite a discovery when it happened, when Kolmogorov decided how to do this kind of description. Well, and indeed, there are 2 types of dealing with things. One is Kolmogorov's frequentist approach, when the probability is defined as a relative frequency, well, the number of positive outcomes out of all. But there's also a so-called Bayesian approach, which is more subjectivist and starts from so-called prior probabilities, which are derived from some kind of previous knowledge, or is so-called uninformative and comes from just a set of known distributions. But actually, even when we are choosing more or less uninformative prior, then it's quite useful to know what kind of seemingly uninformative priors we can take, because even well-used distributions, they in fact have quite strong underlying assumptions. And to understand those assumptions, we again just need definitions. So let's move on towards the definitions. So firstly, we need to define what is a random variable at all, because then we will describe the distribution of a random variable. So random variable is just a function that converts probability space into numbers or real numbers. And in this case, for any particular number, we'll be able to define a probability. All nice and easy. So if we are in a finite case, then this random variable is called discrete, and then we can easily define the probabilities. And if we can define the probabilities, that means that we can define probability mass function. So probability mass function basically is just the set of those probabilities, so that a probability is defined for any value of our random variable with the important property that they sum up to 1. And usually we just deal with random variables, sort of missing the step of defining the very basic blocks of basic probabilities and the initial space. And we just consider, in fact, a random variable, which is then a pair of all possible values of this random variable and all possible probabilities. So that's how we define a discrete probability distribution. Now, another important thing that is defined approximately at the same time is the expectation, also called first moment. So the expectation is defined very easily for discrete variables. It's just the product of a probability and a relevant value, a relevant number. And as such, we can see the expectation as some kind of a weighted average that takes probabilities a weight and then finds the weighted average of all possible values v. And from the average, we can, as always, derive the variance using this kind of formula. Well, there is another type of this formula for the variance, but I'll leave it for now. And let's try to apply it to a well-known problem. Let's start with this problem first. So suppose we have 36 tickets, and suppose we say that 5 of them are winning and will yield us a price of 6. But all other tickets will ask us to pay £1. So what do you think? Is it worth playing this game? What do you think? Yes or no? What do you think? You're welcome to try to compute it, or you can just guess and say Yes, you think it's worth it, or no, you don't think it's worth it. No. Good answer. Anyone else? Oh, by the way, you're welcome. Guess is no. Well done. Well, yeah, so let's move on and let's see the solutions. Let's put some maths behind our initial guesses. Yeah. So what we are trying to find is the expectation of the win. So our random variable is now the win. So what possible values can our win take? It can be either -1 or it can be +6. And I think I can spot the typo in there. We can see it. So what is the typo on this slide? Can someone see it? You're welcome to write in the chat, or you can just voice it. Well, it can be +5. You see, there are indeed two possible answers or two possible values of win. Either indeed -1 when you pay 1, or indeed +6 when you are paid 6. Yeah, but what are the probabilities of those? The probability of -1 is not 536 as written in here, it's 3136, yeah? And the probability of win is small, which means that on those green bars, -1 and 6 should be just swapped over. But if you do that, then we indeed will get the sort of correct distribution. We can have +6 with quite a small probability, smaller probability of win, and we can have -1 with a larger probability. And to get the expectation, we just need to multiply the probability by the value, which means that the formula is correct, not based on the correct picture, but the formula itself is correct. And it's indeed 5/36 probability multiplied by the value 6 plus 31/36 probability multiplied by the value -1, which gives us -1/36. So the expectations of the win is minus something, which means that the expected value of win is unfortunately negative. So well done everybody who guessed that it's not the best game to play. Okay. Well, that's another example for you. So the similar question, will you buy a ticket for £3 if you will win the number of parts that is equal to the number of dots? So what would you reply? Yes or no? So you can win the number of dots, which means that you can win 6, but you can win 1, which means that it's not a stupid question. Okay, yes, very good. So let's have a look. So now the expected value will be the number of dots, which is 1, 2, 3, and so on 6, multiplied by the relevant probability each. And if we are dealing with a fair die, then indeed each of the numbers should be multiplied by 1/6, which will give us the expected value 3.5. So yeah, again, you're absolutely right. That is something probably worth playing. A similar question. What then is the most probable amount to win after one roll? Because you see 3.5, you can't really win this amount. You can win 3, you can win 4, you can win 1, you can win 6, but not exactly 3.5. So what is the most probable amount to win? What do you think? Yes, very good, Daniel. Indeed, they are all equal probabilities, which means that all probabilities are equally likely. And that confuses people actually quite a lot. Because that's again brings us to the topic of our first probability session when we compared different descriptors. And here, expected value is the mean, and the most likely value is the mode. And because those are different from time to time, then indeed, the most probable amount is not the same as expected amount, which can be sometimes confusing. Okay, now a slightly trickier game and a slightly more famous one is this one. Suppose you are suggested to play the following game. You keep flipping a fair coin until the first head. And you win is 2 to the power of n when you had this first head. For example, if it was tail first, then head, then you will win after 2 flips, and you will win £4. And the question is, how much will you be willing to pay this particular game? Well, would you like to make any suggestions of your favorite sum? Just any. For example, would you be willing to pay £1 or maybe none if you think that it's not worth playing this game? Well, yeah, that is a tricky one. And if you are trying to find the expectation, it might take time. So let's do it together. We know that flips are independent, which means that to get ahead after each next flip, we need multiply by a half, which means that for the n flips, the probability will be 1/2 to the power of n. What is the expected value in this case? So every next probability is 1/2 to the power of n. What is the expectation? So for the first head, it will be, will win 2 with the probability a half, which will be 2 multiplied by a half. For after 2 flips, the probability will be 1/4, as mentioned here, and the win will be 2 to the power of 2. Okay, and then for the next flip, the probability is 1/8, is written here, and the value of the win will be 2 to the power of 3, and so on. So what is the expectation or expected value for this case? Yeah, it's a tricky question if you don't know how to write it down, but it's possible to do it in one word. So what is the expected value? Okay, so the expected value, as mentioned, will be a half multiplied by 2, quarter multiplied by 4, and so on and so on and so on, which will give us a larger and larger number. Potentially infinite if we are playing infinite many times. And that's interesting, isn't it? Because that means that our expected win is potentially infinite, which should mean that this game is profitable for any price that we can pay to play it. But that's a strange answer, isn't it? Because, well, that means that a fully rational player will be willing to pay even 1 million because their expectation to win is infinite. But that's surprising, isn't it? Why? Well, let's have a look. Because again, another attempt is to mix up the expected win with the probability of doing so. So let's try to compute the probability of winning this million. How many tails before the first hand should we get to win indeed more than 1 million? And let's try to compute. We need to find the minimum integer such that 2 to the power of this integer will be larger than 1 million. And 1 million, let me remind you, is 10 to the power of 6. And here is a hint for all of us. If you remember that the kilobyte, which is approximately 1,000, or 10 to the power of 3, a kilobyte is 2 to the power of 10. So if we know that 10 to the power of 3 is 1,000, then 10 to the power of 6, what will it be as 2 to each power? What power of 2 will give us 1 million? Yeah, very good, Daniel. Thank you very much. And that's indeed will be 20. So we win 1 million after just 19 tails. So is it a probable event? Well, probably not very. The probability to have this 19 tails is 1 over 2 to the power of 20. So that's an interesting sort of contradiction. The probability of having something and the expectation of getting the result, because the expectation requires us to be able to continue doing the same thing infinitely. And that's the first sort of contradiction to our senses when we start dealing to non-finite numbers for today. And that brings us to the way, or to the necessity of a way to deal with infinite numbers somehow. And it turns out that we can indeed use probabilities to define everything else, all the probabilities that we need, even if we cannot pinpoint every single probability. Because the probability of having a random value being smaller than some number is enough to express all possibilities. So if we know this probability of being smaller than something, then the probability of being larger than something is obviously just 1 minus this probability, and that's trivial. And then the probability of getting in the interval, I hope we all understood that, is just the difference of probabilities. And that's a very simple thing, but it was quite a discovery that allowed the existence of contemporary mathematical statistics and probability theory, because that's where the cumulative distribution function appears. So the cumulative distribution function of random variables define just that. That's the function that is equal to the probability of this variable being smaller than some value. And if we think about that, it's a very clear and intricate way to avoid this pinpoint probability definition in a single point. We do not do it by points anymore. We do it for half of the line, which means that we can do the same kind of definition of cumulative distribution functions or probabilities for continuous numbers as well. Well, let's quickly discover some or cover some properties of this distribution function. Well, firstly, because we say that this function is probability of getting up to this number from minus infinity, that means that if our numbers grow, then the function grows as well. And that's why it's called cumulative distribution function. It sort of accumulates probabilities. Secondly, for minus infinity, this function is 0, and then the maximum value is 1, because we know that probabilities cannot be larger than 1. And then the function is just increasing from 0 to 1. And the third important property is the one that we've just discovered, that we can define any probability from any interval from this function. So let's apply, and that is why this cumulative distribution function is one of possibilities to define any random variable or any distribution. So let's define some simple variables. So the first simplest one is uniform discrete variable. And that's exactly what we get if we throw a coin or a dice. A uniform discrete variable just has equally likely outcomes with the same probability. And the first attempt to define this discrete variable was just from the probabilities, or so-called probability mass function. And there's just a plot for the case of 4 n equal to 4. How is mass function connected to the cumulative distribution function? Well, as mentioned, cumulative distribution function accumulates probabilities, which means that cumulative distribution function was 0. Then at point v1, the first value, it will jump by the value of probability in v1. At the next point v2, it again will jump by the value of this probability, and so on and so on. And the largest value that it can jump to will be equal to 1. That's how it looks like. Well, be careful a bit, because we can have those arrows pointing either to the left or to the right. Well, sometimes it's not arrows, sometimes it's an empty an empty dot, and that is defined by the agreement how we take our cumulative distribution function. Basically, mainly if it's probability of being smaller than this value as I defined it, or if it's the probability of being small or equal to the value. And by the way, that's, as far as I understand, that is difference between sort of Western school and more Eastern school. So one of the schools take strict inequality, and another one prefers non-strict inequality. Sometimes it's worth checking. That is also illustrated in this example. So what will happen if we take more and more and more experiments? So for the dice, we had just 6 possibilities, and then cumulative function looked like that. But this strange dice with 10 possible sides will produce also uniform distribution from 1 to 10. The probabilities will be smaller, obviously, to the up to 1. But cumulative function, it looks interestingly similar, doesn't it? It goes follows the same line. same trend, like along the straight line, and the steps between each value is getting smaller and smaller and smaller. And that's how the idea of making a continuous variable out of it appeared. Now that's how the uniform continuous variable was introduced. So a random variable is called uniform continuous on some interval of from A to B if it can be defined by this cumulative distribution function, which is given by this formula and shown as blue line in the picture. So it's 0 at minus infinity, 1 at plus infinity, and then in the middle between A and B, it just changes continuously between 0 and 1. Well, and the formula is written here. And in fact, we are doing this with a beautiful thing in here. When we sort of approximate or move from finite distribution and finite dimension to infinite ones, well, we're dealing with changes. And if we are dealing with changes, that means that we are dealing with calculus. So let me give you just a brief informal introduction that in calculus there are two important values. The first is derivative, and derivative is just the rate of change, which can be depicted as just a gradient of the line. So what is depicted here, we have two dots, and the line that goes through them is this red line. But if we move the dots together closer and closer, then at some point it becomes a tangential line or gradient, and that's what a derivative is about. And what is the inverse of a derivative? That's the question to you. What is the inverse of a derivative? Yes, thank you very much, Daniel. You've answered before I even typed it in. Yeah, indeed. Inverse is the integral, and the meaning of the integral is also connected to the curve, but it's the area under the curve. And there is a so-called fundamental theorem of calculus that connects derivative or the gradient with the area, which is with the integral, which is the area under a curve. Yeah. Why do I say that? Well, because it turns out that that's exactly what is used in probabilities when we especially deal with continuous distribution. Because this idea of having an area or an integral which is somehow connected to the line, to the curve, or to the shape, is the idea behind so-called density function. So, probability density function formally is just a derivative of a cumulative function. So let me remind you again that cumulative function was a probability. That's the sense of it. But it turns out that probability density function can be derived as a derivative of this probability. And then it has quite a nice sense of represented density. Why? So for the uniform variable, just by taking a formal derivative, we'll get to that probability density function, so-called PDF. And then we can see that if we depict this function will represent, well, a 0, then a line at this height, then 0 again, such that the area under it will be equal to 1, to the maximum possible probability. And the question is it just a coincidence? Well, not really. Let's have a look at how they all are connected. So here's the PDF, the density on the left, and cumulative distribution probability function at the right. So to start with, at minus infinity, the cumulative distribution function is 0, and the PDF in this case is also 0. Now, what happens if you start moving between A and B? If you start moving between A and B, our cumulative function starts growing, which means that its derivative will start growing as well, and it will form the area under the distribution, under the density function. And the same will happen on the all integral from A to B till it reaches the peak. And the peak, as we all remember, is the maximum probability of 1. And then our distribution basically ends, and our cumulative density has reached its full potential of 1. And as we all know, to define the probability of getting between 2 points, which is green here, then on the right picture, it will be just the difference of values in cumulative function between 2 points. And in the left picture, because it's a derivative, it should be the area under the relative density. So actually, sometimes it's easier just to visualize this area rather than compute the formula for a cumulative probability. That's why to define any kind of random variable, usually you will get 2 possibilities, either the density function or cumulative distribution. So let's try to use them both on this simple example. Suppose we have a uniform variable on the interval from 1 to 5, and suppose we want to find the probability of getting between 2 and 4. And let's try to do it in both ways. So firstly, for a cumulative function, we can write down this formula and then just apply and get this probability. But let's try to do the same thing from the density and from the areas. And I think it's quite self-explanatory, isn't it? We can also write down the formula. And most importantly, we can sort of quickly visualize the density of this distribution and the area that we need to take out of this density. So the area under the curve. So that's why probably density function is even more widely used than cumulative distribution function. So each of them have their own place. Now we have everything to define the general case of continuous variable. So the variable is called continuous if its cumulative distribution function is continuous. Let me notice that the density does not have to be continuous. Well, exactly what we have with uniform variable, right? The density function was not continuous. It was a sort of step function here. But the CDF distribution function is a continuous function. And then quite often we also get a density function because, well, it's picturesque and we can define it. Yes, thank you for letting me know. Yeah, sure, that's fine. But we are actually moving to the more interesting bit of considering some examples of distributions. So the first well-known example is an example of so-called Bernoulli distribution. And that's what we deal with when we throw a coin, especially if this coin is not a fair one. Because Bernoulli distribution describes variable with 2 outcomes, with each outcomes having some kind of probability, which we call parameter. And if we know this parameter for one of the outcomes, P, then quite obviously the probability of another outcome is just 1 minus P, but it's often defined as Q, just to ease up writing down some formulas. And here you can see the probability mass function, which is just P of 1 minus P. What is also interesting is the expectation. We can find the average, which is just, well, just that P. So the expectation for the Bernoulli is indeed just the probability of getting a positive result, one of the outcomes. That's a very, very, very basic block of distributions, of many distributions, in fact. And it is used in the next distribution. The next distribution is so-called binomial distribution. So binomial distribution is just the number of successes in independent Bernoulli distributions. And again, parameter is just the probability of success. Then the probability mass function, it can be defined by a binomial formula, and choose K. That's why the name binomial. So the probability mass function, which is analogous to density or just the probability, is defined by this formula. And here, again, the expected value will be similar to the previous case, just probability P repeated 10 times, which is NP. And here I did not write the cumulative distribution function because the formula for the cumulative distribution function is slightly longer. But I've just represented the pictures. So on the left-hand side, that's the mass function. On the right-hand side, that's the cumulative distribution function. And as you can see, for large numbers, it's just the collection of similar what we saw before for the dice throws. That's what we all probably already know. But the next distribution is slightly less canonical. It is so-called hypergeometric distribution. And hypergeometric distribution is also the number of successes and also in n repetitions. But this time, those repetitions are not independent. It's the draws without replacement. Which means that to avoid total exhaustion, we need also to give the size of the population and also the side of sort of possible positive objects. And in this case, it's again a distribution where a discrete distribution where we can define any probability. And the probability mass function also has this form. And then in the picturesque representation is quite similar, just a bit steeper if we compare them all together. So that's the binomial distribution, that's the hypergeometric distribution. So the shape is similar, the formula is slightly different, and the expected value is also slightly different. Instead of NP, it's NK divided by N. Not much difference here, isn't it? So if you're having not independent events, just use this hypergeometric distribution. The next one in my list is so-called geometric distribution. So geometric distribution can be in fact defined in two ways. It's either the number of trials before and up to getting the first success, or it's the number of failures before this very first success. So basically, it's the number of throws that we need to try before succeeding. And it turns out, as we can think about it, the mass function will be equal to y minus p, all non-successes, to the power of k minus 1. If we have, if we are getting the success on the k step, multiplied by the final success probability of p. And here again, it's the probability mass function, and cumulative distribution function looks like that. So if you're computing in exact numbers, the number up to getting the first success, that's the distribution for you. But that's all finite distributions. And quite often we are interested in infinite case and, well, in more smoother distributions, especially if we are dealing with large numbers, similar to what happened to uniform distributions when we increased the number of trials. And for that, in fact, in most of the distributions, this specific function takes quite a large role. It's called exponential function, and it is depicted from the real number e, which has this kind of value, and it's similar to pi in the sense that it also can be written exactly with all the numbers behind it. It's transcendental. The most important property is that it is the only positive real number that is stable under differentiation. Now that's the absolute uniqueness of that exponential number and exponential function as well. Now that is why we bump into exponential again and again and again, because we are mostly interested in changes, we are interested in derivatives, and hence having this unchangeability under derivation, basically being stable, is so unique and important. And that value allows us to immediately introduce so-called exponential distribution. An exponential distribution have this formula for probability density function. It's just some parameter lambda multiplied by exponent to the power minus lambda x. And it has a meaning. So exponential distribution describes time between events, but not any events in a so-called Poisson process. And Poisson process, by definition, is the process when events occur again and again and again without stopping, not a final number of events, independently from each other with a constant average rate. So if we have some repeated events again and again, then the time between those repeated events can be multiplied by or modeled by exponential distribution. And here's the formulas and plots for them. Well, but let's go one step back and let's have a look at the Poisson distribution. So Poisson distribution again is the number of events that occur independently if we know that they occur at some constant average rate. Yes, and by the way, obviously, yeah, that's right. And then we can define the probability mass function by this formula. So that will be this rate multiplied by e exponents to the power of minus this rate divided by k factorial, where k is the number of successes. And also it turns out that the expectation is obviously equal to that parameter lambda, because it's indeed just an average rate, which means that expectation is indeed the average and is this parameter. So probability mass function looks like that, and cumulative distribution function, you see, it's not very interesting, isn't it? Because what we've seen so far is probability mass function and density function having quite different shapes, yeah? But, for example, in here, quite a substantially different shape. And cumulative distribution function, well, it's not very interesting. It just grows from 0 to 1, and not much can be seen here. So Poisson distribution is very, 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 very famous because it can be applied to lots of different situations, especially when those events are rare. And here are some examples. One of the very famous examples, like a training example, is just a number of phone calls that reach the phone station in say, a minute or an hour. But also it can be used to model different similar things, including the number of photons hitting the detector. And it's also useful because if we know the average rate instead of the average number, then also the formula is quite slim and easy. And also it's famous and convenient because of the connection between the Poisson distribution and the binomial distribution that we all get used to. It turns out that if we increase the number of trials or events and decrease the probability so that the average will be still constant, or our parameter is constant, it turns out that in this situation, the binomial distribution will approximate to by Poisson distribution. And as a rule of thumb, we can just apply this formula for large numbers larger than 100 with NP being smaller than 10, which is very handy and relieves lots of calculations for binomial distribution. So Poisson distribution is indeed famous, and again, it's connected to the time between of the events, which is exponential distribution. Any questions so far? So I think I have 3 more distributions. And 3 more distributions, they're slightly, that's the main bit of what I wanted to say. And 3 more distributions are a bit more stranger. So the next one is gamma distribution. And in fact, it's some kind of generalization of exponential distribution. So if you remember the meaning of the exponential distribution, you can sort of get a feel for what gamma distribution is. So let me compare the pictures by moving a bit back. So exponential distribution, the most interesting thing was density, yeah? And it was steadily diminishing from the large number to getting smaller and smaller, smooth function like that. So let's have a look how gamma distribution looks like. Can you spot exponential distribution in the picture of density functions? Yeah, I think you can, right? That's red line or a purple line. And that's because indeed, for those parameters, we get exponential distribution. But if we have other parameters, then we can get other shapes of densities. That's why it's a larger family. And gamma distribution, in fact, strictly speaking, it's a 2-parametric family of distributions. And now it's not just 1 parameter, but 2 parameters. One of them is thought to be describing more or less shape, and another one is describing the shift of the distribution. And the probability mass function is just written in here. And this gamma is the gamma function, and I'm not introducing the formula for it. What it is useful to remember, though, is for integers, for positive integers, this gamma function is just a factorial of this number -1. And again, similar to the exponential distribution, the expectation is represented in quite a simple way. It's connected to this theta parameter. Okay. So that's, roughly speaking, a generalization of exponential distribution. Another slightly stranger, so what happens in here, what happens in exponential distribution is that the rate is the same, yeah? And what happens if you'd like to change this rate? For example, if you would take into account the possibility of a situation when defects happen early, well, for example, in population health, it's child mortality that is higher than later in life. So it's a failure rate that decreases over time, but also it can increase over time, which is effect of aging of a person or of a mechanism. And then we can consider another type of distribution, which is called Weibull distribution. And it's also a two-parametric distribution, so the number of parameters gives sort of larger flexibility. And it describes time to failure. And one of the main interesting things there, that the rate of the failure is not constant, and it depends on one of the parameters, as written here. And graphically, the shapes of density function is quite similar to the gamma distribution that we saw before. Okay, and so that's quite a weird one, but it's an interesting one because it's probably the simplest one that allows the change in rate. And another one, the last one in my list for today, is so-called beta distribution. And that one is particularly interesting because it is limited. So previously, well, uniform continuous distribution was limited, right? It was on some kind of interval, but then exponential distribution and many other common distributions are not. While beta distribution is another way to get this limitation to an interval, which can be quite handy at places and times. So you see, why is it better than uniform distribution? Well, because it's smoother and it can take different shapes. So it's not just a step function, not just a single value, but we sort of smoothen different values in between 0 and 1. Well, again, the formula for the density function is a bit complicated, and it contains so-called beta function, which I'm not introducing. You're welcome to look at the formula if you need to. I'm just getting the feel of what's available and when. So that's all in my distributional zoo. And actually, I don't know, can you see? Maybe not. Can you see an additional screen that I've opened now? No? Okay, I'll stop sharing. No, I'll share another screen because I didn't know it myself, but I think it's quite useful, quite a useful knowledge. Apparently, there exists so-called probe onto, and it's ontology of all probability distributions, which can be particularly useful if you are choosing between distributions, say, for Bayesian analysis or something like that. And it's amazing because it tries to depict all kind of interconnections between different distributions. And I think it's just awesome because then if you look at it, you can just try to see how to get from one distribution into another, for example, increasing the number of trials if we did with Bernoulli distribution or changing some parameters. So here it is all interconnected in one map. And I've just recently discovered it, and I think it's just amazing. Well, and the simpler thing can be also, I'm sharing my slides again, the simpler thing can be also found on the relevant wiki page. So do spend some time there. By the way, so we've discovered quite a zoo of different distributions. Can you say what I missed? maybe also looking at that ontology picture there. There was some distributions which probably heard about, but I obviously missed today. Can you maybe mention them? What distribution can you name that I didn't cover today? Yes, great. The normal distribution, which was actually right in the middle of that probabilities ontology page, because it's sort of everywhere. And it was intentional today, because normal distribution will be the topic of our next session, when we will cover normal distribution and closely connected, which is logistic distribution, and also logit, which comes from logistic distribution, probit, which comes from normal distribution, and obviously also some elements of hypothesis testing, because that's what the normal distribution is used most of all. So today it was the zoo distributions. Next time we are dealing with normal distribution, but after that, on the last session for this year, we are again moving from normal distribution to real life and showing why the life is not normal. But that's all for today. And just as a homework and to keep you busy this week, there's a problem which is also known as boy-girl paradox. Try yourself on that. That's all for today. Any questions? Sorry for getting all the time. So any questions about distributions or about anything else? Yes, it's a good idea, by the way, to stop the recording.
Yeah, there was a request about recording. Yes, we can